Good morning. So I thank the organizers, Sivashish and Niharika, for this invitation. I'm also grateful to PSG Tech and various of functionaries of the ACM for all the efforts in organizing this event, especially Prof. Dr. Ranga Rajagopal, who's taken care of me. And so I was looking at the plan for the program, and it's really very admirable that it tries to provide support for people who are engaged in research in computing science. My talk is probably not the best for the occasion, but I will do what I can. But I assume that later talks will give you more to think about. The other thing is, of course, the previous talk in Coimbatore was given by Mr. Amit Shah. So I hope what I say is at least more relevant than that. Also, I will sit down and give my talk. I don't mean any disrespect. It's just that I need to write on the board. And my choice of this non-standard medium for the talk has also made demands on the AV team. So I'm grateful to them for accommodating me. Thank you. So I'll sit down, and it will be a usual classroom lecture, which was meant to be given on a board, but I'm giving it on a tablet. Yeah. Please ask questions, and let us see. Yeah. So the title of the talk is Side Benefits of Knowing an Algorithm. The reason the talk is named this is the following. In Bangalore, every first and third Saturday, there is this thing called math circles, which is for high school students, even middle school and high school students in mathematics. And I was asked to conduct a session in which I told them about a theorem. And then one of the school boys, he asked me a question to which I did not know the answer immediately. Okay. And then it turned out that an algorithm that I had learned 40 years earlier somehow helped me arrive at an answer. Okay. So in that sense, it is not very original research. I mean, all that I'm saying can be found if you just Google or even ask ChatGPT. But I decided not to do it. Please trust me. And I would like to tell you what the problem was and how it went. Okay, good. So my goal is to tell you a theorem that I told those school children, and then the algorithm that I learned 40 years ago, and a formula, which is a very important formula in mathematics, and how these are connected. Okay. So, yeah, but again, as I said, please ask questions. Now, yeah. So these slides are also available at this site. So since this is not a board talk, many things will vanish from the screen as I move. So if you would like to scan this and keep it on your phone, and you want to go back, you can do it on your phone. That way, when you are looking at the phone, I will assume that you are interested in my talk and not something else. Yeah. Okay, but it's up to you. I'll just wait a minute. Yeah. So I hope it takes you to the right site and doesn't show you. Okay. Yeah. So because I'm not sure my handwriting and my screen is visible from the back, but nevertheless, yeah. Okay, so should I move on? Yeah. I'll move on. Yeah. Okay. So, yeah. So the plan is to tell you about a theorem, an algorithm, and a formula. Okay. So these are about sequences. So what's a sequence? Well, you have some domain like 1 to n, and you pick elements from this domain and write them down, and that is a sequence. Is it clear? Yeah. Okay. So here n is 5, and I have made a sequence of the numbers 1 to 5. Sorry, somehow 2 vanished. Yeah, sorry. Yeah, there's meant to be a 2 too. Yeah. So maybe 2. Yeah, I don't know. Okay, good. All right. Yeah, so the numbers 1 to 5 are listed in some order, and we assume that the numbers are all distinct. Okay. So that's what I mean by a sequence. Now, what do I mean by a subsequence? A subsequence is you take this sequence and put only some of its elements and remove the other elements. Okay. So if you have a sequence, drop some elements, leave the others, it's a sequence, but leave the others in the same order. Okay. So for example, here n is 16, and I assume I have put the 16 numbers here in some order, and this 12, 14, 16, 1, 11, 6, 9 is a subsequence of this sequence. This sequence is called S, the subsequence is called S prime. Okay. So 12, 14, 16, 1, 11, 6 and 9 in the same order. Okay. So I hope everybody understands what a sequence is, what a subsequence is. Okay, good. An increasing sequence. An increasing sequence, these are numbers, it's a sequence, but the second one has to be bigger than the first, the third one has to be bigger than the second, and the last one has to be bigger than the second last. It has to be increasing. If you like to draw histograms, then it should be increasing like this. That's what I mean by increasing. And a decreasing sequence, so decreasing sequence is something like this, where things reduce. So is this clear? So this 3, 4, 7, 8, 11, 15, it appears here, 3, 4, 7, 8, 11, 15. It's a subsequence of the original sequence, and it also happens to be increasing. Okay, good. By the way, I don't see any clock, so somebody has to stop me. Yeah, so tell me 15 minutes before. Yeah. And similarly, this one is a decreasing subsequence of this sequence. So is it clear? So far what have I told you? I've told you what a sequence is, what a subsequence is, when do we call a sequence increasing, when do we call a sequence decreasing. This is all we have said. Okay, everything okay? Good. So there's a theorem from 1935, and let us read it together. So every sequence of k squared plus 1 distinct numbers has either an increasing sequence of length k plus 1 or a decreasing sequence, sorry, what happened? Yeah, of length k plus 1. Is it clear? If you take k squared plus 1 numbers, then inside it, at least you will find one increasing sequence of length k plus 1. And if you can't find an increasing sequence, then there must be a decreasing sequence of length k plus 1. Things cannot be completely jumbled. There will be some order somewhere. For example, here are 5 numbers, yes, and you can find either an increasing sequence or a decreasing sequence. What can you find? So what is 5? What is k? 2. So we need an increasing sequence of length 3 or a decreasing sequence of length 3. And can you find one? Yeah, 5, 3, 1, yeah. So you found it, theorem is not false. Okay, good. Yeah. So now why is this true? Why is it that whenever you take a long enough sequence, either you will find an increasing sequence or a decreasing subsequence? This was the problem that I wanted to discuss with the school children in Bangalore. Okay. The Erdos-Szekeres theorem. Okay. So, so why is it true? So I want to give you the proof. So I'll wait a minute, you read what is written. Yeah, so suppose somebody gives me a sequence of length k squared plus 1, and I want to prove that there must be either an increasing sequence in it or a decreasing subsequence in it. So what do I do? With each of these numbers, I associate 2 numbers, Ri and Ci. Okay, Ri is the length of the longest increasing sequence, subsequence starting at Si. So if you take some SI here and find out which is the longest increasing subsequence of the original sequence which starts at there. And CI is the length of the longest decreasing sequence that starts there. Is this clear? Yeah. So with each number SI, I am associating an RI and a CI. Okay. And then here is this infinite array, you can say 1, 2, 3, 4, k and so on, 1, 2, 3, 4, k and so on. So if this number SI, I ask what is the longest increasing sequence, what is the longest decreasing sequence, and move this SI to that position. Is it clear? Okay. So for each element, ask what is the longest increasing sequence, what is the longest decreasing sequence starting from there, and move it here. Okay. The important point is that if you take two elements in this sequence, both Ri and Ri cannot be, so the Ri and Ci values cannot both be equal for both of them. Is this totally obvious? If there are two sequences, suppose the longest increasing sequence from this was 5, the longest decreasing sequence was 4. And this another element also says that the longest increasing sequence is 5 and longest decreasing sequence is 4. Well, one of them is bigger than the other. If this is bigger, then this fellow's increasing sequence can be, you can attach it to this, and this fellow's increasing sequence will be even longer. And if it was the other way, this fellow's decreasing sequence will be long. Sorry, things are inverted. You are probably thinking like this, but doesn't matter. Yeah. So, yeah. Is it clear? The two different elements cannot have the same Ri and Ci values. Good. Now there are how many elements here? K squared plus 1. How many boxes are there here within this part? There are k squared plus 1 objects which want to sit in different places, but there are only k squared places here. So one of them has to sit outside. Is this clear? But the moment it sits outside, either it has an increasing sequence of length more than k, or a decreasing sequence of length more than k. Is this, did everybody understand? Will you go home and tell your nephew? Yes? Yeah? Yeah? Great theorem. Yeah? That if you take k squared plus 1 elements, attached to each number an Ri and a Ci, each number gets a unique pair Ri Ci. There are only k squared pairs available here. So one of them has to use a pair outside. The moment it uses the pair outside, that means either its Ci value is more than k or its Ri value is more than k. Is this okay? Yeah, good. So now, is k squared plus 1 the best possible? Yeah. The question is that is, yeah, so this proof needed k squared. But maybe, there are people cleverer than these, unlikely, but who get they don't need k squared plus 1. They manage with k squared itself. Even in a sequence of length k squared, there is an increasing sequence of length k plus 1 or a decreasing sequence of k. So in that sense, I'm asking, is k squared plus 1 the best possible? Or in other words, are there sequences with k squared numbers that have neither an increasing sequence of length k plus 1 nor a decreasing sequence of length k plus 1? Can you construct such sequences? Now it turns out that you can construct such sequences, and let me show you how. And this was the exercise for the school children. Okay, show that k squared plus 1 is the best possible. So here is one way. Take the numbers 1 to k squared. Yeah, because we are trying to show that k squared plus 1 is best possible. That means with k squared you cannot get this done. Now take the first k and move them to the end. Yeah. So can I do that? Yeah, let me try. Yeah. So I move them to the end. Then the last k, I move them in the front. You understand? So what the last k I move here, and the first k I move here, the second k I move next to it, the third k I move next to it, and so on. So what is the sort of pattern you get? The pattern you get is this, then the next one is this, the next one is this, and the last one is this. Do you see that? Yeah. So temporarily it is increasing, but then it falls. And then it falls. So it is like this sawtooth sort of thing happens. Now look at this sequence. In this, if you pick k plus 1 elements, some 2 of them will fall in the same block. But that means they have to be increasing. Yeah. So you cannot get k plus 1 which are decreasing, because some 2 of them will have to be in the same increasing block. Yes. And if you again get k plus 1 and hope that they are increasing, well, you will have to touch 2 different blocks, and the moment you touch 2 different blocks, there will be a decrease. Okay, is it? Yes, maybe not very clear. It's not clear to me. Yeah. Yeah. So, okay, good. So I hope you understand. You will be able to construct such a sequence. Yeah. But in any case, 1 second. Here is this sequence. K was 2, and I have constructed 4, and you can see that the last block 3, 4 I have moved to the front, and the 1, 2 I have moved back, and you cannot get an increasing sequence of length 3, and you cannot get a decreasing sequence of length 3. Okay. And you could have turned this around and done it in the opposite order. That is, you first could have listed all the numbers in decreasing order, and then move the last block first and the first block last, and keep exchanging like that. Yeah. So this is another example. This is one example. This is another example. Okay. So k squared is best. Question? I'm not sure if I missed something, but can you put it like 4, 1, 4? Yeah. Sorry, 4, 1, 2, 3. Let me try. Let me write down. The suggestion is 4, 1, 2, 3. Yeah. This is an increasing sequence here of length 3. Sorry, the question was, would 4, 1, 2, 3 also do the job? Yeah. It doesn't, because 1, 2, 3 is an increasing sequence of length 3. I don't want any increasing sequence of length 3, but thank you. Yeah. So I'm sure the same question was there. So, yeah. Others were shy. Yeah. Good. Okay. Sorry. What to do? I don't know what it does, but anyway. Yeah. Is it clear? Is the question clear? Yeah. So, but then, yeah. But there are other sequences. For example, this and this. Okay, it doesn't quite fit our pattern, but these also don't have increasing sequences or decreasing sequences of 3 elements. So the student actually, after this exercise, one of the students told me that these are the only 2 examples. Okay. And then we discussed a little bit, and we said, no, there are other examples. Yeah, so there are other examples. Sorry, this was our original example, and these are other examples. And the question is, how many examples are there? Is the problem clear? There is a theorem which says that if you take k squared plus 1, then you will get k plus 1. We also checked that if you take k squared, you can arrange things so that you don't get k plus 1. But how many ways are there to arrange k squared numbers so that you don't get a sequence of length k plus 1? How many ways are there? Okay, this is the question. So let me just, yeah. So actually I'm done with my theorem. Okay. Yeah. So, and we are now left with the question, how many such sequences are there? Okay. So, I'm sorry, something went wrong. Yeah. So I forgot to tell you this. So that I don't run out of time, I'm going to call such sequences saturated sequence. Saturated sequences means they are of length k squared, they don't have an increasing sequence of length k plus 1, they don't have a decreasing sequence of length k plus 1. But the moment you add one more number, you will get k plus 1. Why? Because the theorem has been proved. Is it clear? That's why I'm calling it saturated. Is it okay so far? Good. Okay. So now the student asked me, or at least challenged me to think, how many such sequences are there? And it turns out that an algorithm that is taught in school, in colleges, in computer science algorithms courses under the heading of dynamic programming, yeah, that somehow helps you answer this question, and that is what I want to show you. So, how many minutes have I taken already? 25 minutes are over or left? Over. Okay, good. Yeah. So, all right. So, I want to now remind you of an algorithm which, given any sequence like this, tells you how to find the longest increasing subsequence. Somebody gave you some sequence and you want to find the longest increasing subsequence in this. Okay. So, here is how the algorithm works. This data S1, S2, Sn will be moved into rows. Okay. And in each row, the numbers, so some of these numbers will be moved to the first row, some to the second row, some back to the first row, some to the last row, and so on. Yeah. But each row will be always decreasing. Okay. What is the rule for moving these elements to these rows? They are written here. So let us read them. The first number will be moved to the first row. Okay. Then whenever you get a new number, you have to find a row for it. How do you find the row? You find the first row where it fits. What does it mean it fits? The row should continue to be decreasing. If it is bigger than the last element of the row, you can't put it there because all rows have to be decreasing. This is a law. Yeah. We will ensure that all rows are decreasing, and whenever we move an element, we try to move it to the row where it fits. Yeah. So I'm going to show you an example. Yeah. But is this clear? So move S1 to the first row, move Si to the first row where it fits, and if Si fits in no existing row, create a new row for it. Okay. So let's do it. Yeah. So, okay. So where should I move 3? To the first row, 8, second row, yes, 9, yeah, it doesn't fit, yeah, 2, very good, you become experts, yeah, 1, 6, 7, 4, 5, is that okay? Yeah. Yeah. So, yeah, I didn't cheat. Those were the numbers. Yeah, good. So, okay, so these rows were actually not used. Yeah. Now, let us ask, why was this element 5 put here? Because there was an element in the previous row which was smaller than it. Yes? And it was already there. And why was that element in the second row? Because there was an element in the previous row which forced it in the second row. That means if I question this fellow, he will point to somebody and that fellow will point to somebody. So if there is any element which appears in row 7, that means there was an increasing subsequence of length 7. Yeah. Is this clear? The only reason you touch the 7th row is because that element can blame somebody in the 6th row, and that element can blame somebody in the 5th row, etc. And blaming means you are smaller than me and you came before me. That means all these elements together actually form an increasing sequence. Okay. So this is the algorithm to find the longest increasing sequence. You run this algorithm, move the numbers down, and find out which is the last row which is populated. Okay. So here are some claims about the algorithm. Every row contains a decreasing sequence. Is it clear? Every row contains a decreasing sequence because that is how the algorithm asks you to do that. Yeah. And if row L is the last row where there is an element, then there is an increasing subsequence of length L. That's what we argue. The claim is there cannot be a increasing sequence of length L plus 1. Why is this algorithm correct? Yeah. Well, you see, all the elements have been arranged in L rows. If there were L plus 1 elements, two of the elements must, if there are L rows and L plus 1 elements, then two of the elements must fall in the same row. But elements in the row are decreasing. So any increasing sequence cannot afford to put two elements in the same row. And all the elements have been classified into just L rows. That means there cannot be an increasing sequence of length L plus 1. And we have found one of length L. So this algorithm is correct. So not only does this algorithm, not only is this algorithm correct, when it finishes, it actually gives you a proof that it is correct. It decomposes the data into L decreasing subsequences, which is a proof that there cannot be an increasing sequence of length L plus 1. Okay. So good. So that's where we are. I don't know what happened. I don't know. Yes, this was supposed to. I don't know what happened, but anyway. Yeah. Can you read? No. Okay, let me try. Yeah, so the algorithm finds a longest increasing subsequence. It provides a proof that its answer is correct, and it also yields another proof of the Erdős-Szekeres theorem. Is it clear? Suppose you had k squared plus 1 elements. Let's go back to the theorem. K squared plus 1 elements. You run this algorithm on that. If you say that you did not hit row k plus 1, that means you did not have any increasing sequence of length k plus 1, then all the data is sitting in the first k rows. One of the rows must have k plus 1 elements, but every row is a decreasing. So if you do not provide me data in k plus 1 rows, then one of the rows will have to be big. Okay. Yeah. So this you can say is an algorithmic proof of the Erdős-Szekeres theorem. Okay. Good. So what? Yeah. So back to saturated sequences. So yeah. So let me remind you. Yeah. All this is fun, but our purpose was to answer the question of the schoolboy. Okay. How many saturated sequences are there? Okay. So let us do this. Suppose somebody gives me a saturated sequence, meaning of k squared elements, and suppose the algorithm is run on this saturated sequence. Yes. How many rows will this algorithm produce? Yeah. Well, it doesn't have any increasing sequence of length k plus 1. So the number of rows can be at most k. But how many elements can it place in any row? K, because every row is a decreasing sequence. So there are k squared elements. The number of rows can be no more than k. No row can be more than k. That means actually each row has exactly k. And the number of rows is also exactly k. Is it clear? If you start with a saturated sequence and run this algorithm, then there are k rows, each with k elements. Is that okay? Yeah. Now, here is what I want you to do. Yeah, so here was this data, and you remember this, we ran this algorithm on this data. And now, take the first row and pack it. Yeah. The second row and pack it. Do you understand what I mean by pack? Just move them to the left until there is no more space. So 3, 2, 1, 8, 6, 4, 9, 7, 5. Okay. Now here is two observations. Each row is decreasing. The rows were decreasing. Packing them are not going to make them increasing. Yeah, nobody is jumping over anybody. Yeah. So this is not a surprise. But do you notice something? Look at the columns. Yeah, each column is also why does this happen? Yeah, or will it always happen when you have a saturated sequence? Do you think the columns will? So what is the process? You take the saturated sequence, run the algorithm, pack everybody to the left. You will get a k cross k square. Okay, so that you get something like this is not a surprise, because each row will have k and there will be k rows. The rows will be decreasing. No surprise there. The columns, even despite all this movement, actually get some nice structure. And let us analyze why. So this is the claim. So when the algorithm is run on a saturated sequence and the rows are packed to the left, the columns will be increasing. Okay. And I would like to do one small proof. Yeah. Okay, so look at row I. It has k elements. Let's call them A1, A2, A3, so on till AK. Then you have row I plus 1, which is B1, B2, B3. Now I want to claim that actually Bj must be bigger than Aj. That is, the columns must all be increasing. Okay, so let us see why. Yeah, so Bj arrived in row J before or after Aj. I mean, you either arrived after or arrived before. Okay, suppose Bj was inserted before Aj. Bj was inserted before Aj. Same old question. Why was Bj inserted before Aj? Because it was bigger than somebody in the previous row. Yeah. But that element is already bigger than Aj, because all rows are decreasing. So this fellow is bigger than this, and this fellow anyway is bigger than this. So we are done. Bj must be bigger than Aj. Yeah. Okay. So what if Bj was inserted? Sorry, this is Bj was inserted before Aj. Now suppose Bj was inserted after Aj. Bj was inserted after Aj. Do you see a problem? Remember, the sequence was saturated. Bj was inserted after Aj. What's the problem? These are decreasing. If you say Bj is smaller, now this is a Bj was inserted after Aj, so Bj plus 1 also later, Bk was even later. Now if you follow A1 to Aj, Bj and this is a sequence and it is decreasing and has how many elements? K plus 1, because yeah, it is picking up 2 elements from the same column. Yeah, but this is not allowed. It's a saturated sequence. So it cannot be that Bj is less than Aj. Okay, so in both cases we are done. Yeah, but actually I cheated. I cheated you a little bit. Suppose Bj was, so now we know that Bj is, sorry, could Bj have been inserted before Aj? Suppose Bj appeared before Aj in the main sequence. What's the problem? Sorry? Suppose Bj was inserted No, it could be that Bj was bigger than some previous element. So, sorry, the suggestion was if Bj was bigger than Aj, then it could be that Bj was, this is decreasing. Sorry, what was the suggestion? It would have been put in the previous row. Well, Bj is bigger than Aj, so yeah, it could still come to the next one. Yeah. But if Bj was inserted after Aj, yes. Sorry, what? I'm getting tired. If Bj was inserted before Aj, look at this. Bj was inserted before Aj. How many? So then this becomes a decreasing sequence with how many elements? Yeah. So that's not possible. So in fact, this doesn't even happen. Bj is always inserted after Aj. Yeah. So the next story is this. You take a saturated sequence, run the algorithm and pack it. You get this. Yeah. Now, for each of these elements, you write down their position in this array. Okay. So 3 appears in which position in this sequence? Position 1. 2 appears in what position? 1, 2, 3, 4. You understand? It's in the 4th position. So you write. So yeah, please help me. So this goes 4. 1 appears in position 5. 8 appears in 2. Yeah. 9 appears in. Sorry, why am I talking about 9? 6. So, sorry, 6 appears in which position? Sorry, yeah, 6 itself. Good. And 4 appears in position? 8. Sorry, 7 maybe. 7, no? Let me count. 1, 2, 3, 4, 5, 6, 7. 8, sorry, good. Sorry, yeah, 8. 9 appears in position, and 7 appears in, and 5, 9. So, because we made this observation that each column is increasing, or Bj was inserted after Aj. Yeah, Bj was inserted after Aj. That means in each column, the numbers that appear will be in increasing order because this element was inserted after this element. It appeared later in the sequence. Good. Sorry, so everybody is restless. My time is up. No. Yeah. Good. Yeah. So you started with this sequence. We ran this algorithm and obtained 2 matrices, 2 arrays. Yeah. This array is called A sub S and this array is called B sub S. And how is this array obtained, the first array? Just take the algorithm and compact it. You got this. And how was this obtained? Just record the positions where it appeared. Now, if somebody erased the sequence and gave you these 2 arrays, will you be able to reconstruct the sequence? It's obvious. Yeah. So the theorem is that if you take saturated sequences of length k squared and convert them into these 2 arrays, then clearly this is a function. From S, you can obtain AS and BS, and you also told me that you can go back. Once you tell me AS and BS, you can reconstruct the sequence uniquely. But actually this is a one-to-one correspondence. Yeah, if you think about it, if you take 2 monotonic arrays like this, in which here the rows are decreasing, the columns are increasing. Here the rows and columns both are increasing. If you take 2 arrays like this and construct a sequence, it will be a saturated sequence. Okay, so this needs a little bit of thought. I'm not telling you why. But that means to count, now I can answer the schoolboy's question. To count the number of these sequences, it is enough to count number of monotonic arrays, but there are 2 monotonic arrays, and square them. Okay, good. So I am done with my algorithm. Sorry, so should I review what we did? Yeah. So we wanted to count the number of saturated sequences. And we said, let us not, it is after running this algorithm and thinking hard, we have figured out that it is the same problem as counting the number of monotonic arrays, but each sequence now gives rise to 2 arrays. And whenever you have 2 arrays, you can construct a sequence. So there is this thing in mathematics called the hook length formula. I mean, people who are interested in combinatorics and counting, if you have not seen this, it is worth attending this talk just for this. Okay. So what is hook? Yeah. So you have a k cross k array like this. Yes. And in that, here is a hook. Yeah, you take any element, travel to the right and go down. This is called a hook. Yeah. How many elements does this hook have? 1, 2, 3, 4. Yeah. And suppose this was the hook. How many elements does that have? 7. Okay. So the number of monotonic arrays according to this formula is, there are total k squared elements. Write k squared factorial in the numerator. And go through all the elements and count their hook lengths. Yeah. And divide by that. That is the number of monotonic arrays. Okay. So this formula tells you how many monotonic arrays are there, and this was figured out in the 1930s, 40s, 50s. Okay. I will tell you the reference. But once you know this, can you answer the question? We just take this and square it. So it turns out that for k equals 3, yes, so we are looking at saturated sequences of what length? When k is 3? We are looking for sequences with 9 elements so that you don't have an increasing sequence of length 4 or a decreasing sequence of length 4. And how many such sequences are there? Well, you do the hook length formula and square it. Okay. It turns out it is 441. 16 sequences of length 16 in which there is no increasing sequence of length 5 nor an decreasing sequence of length 5. For k equals 2, if you do this, the answer comes out to be 4. So the 4 sequences we found were the only ones. Okay, good. So where does this formula come from? It turns out it comes from representation theory. And in the 1930s, Robinson analyzed an algorithm, not this algorithm, a different algorithm, and came up with something which was improved by Stenstedt, and finally Knuth sort of wrote down the properties which now go by the name RSK. Yeah. How many people know what PSG stands for in PSG Tech? Sorry, can you raise your hands? Okay, yeah. So please find out. Yeah, okay, yeah. Okay, so anyway. Yes, sorry. So RSK correspondence, yeah. So RSK correspondence named after this assigns to each sequence 2 tables, yeah. And this is a 1-to-1 correspondence. The formula, the hook length formula, was actually due to Frame, Robinson and Thrall, 1954. And those of you who like probability, there is a probabilistic proof of the hook length formula from 1979. Very nice to read. Okay. So I would invite you to look at that. So hook length formulas work not only for square tables, but also objects like this, which are called Ferrer diagram or Young tableau. Some of you who work in representation theory might have seen Young tableau like this. Yeah, it's straight on the left, but it is somewhat jagged on the right. And the number of ways to fill up elements in this is the same formula works. So for example, here I have 16 elements and I need to arrange so that the rows and columns are all increasing. This is just counting the number, length of the hook. Yeah, this hook has 8 elements, 1, 2, 3, 4, 5, 6, 7, 8. And then you get this formula. Okay, so this is the hook length formula. So I have told you a theorem, I have told you an algorithm, and I have told you a formula, and my time is up. Thank you very much.
Professor Jaikumar, for the very interesting and clear talk.
So if there are questions, I'll be happy to answer. The point, I mean, I don't know your sorry, I'll say some, philosophical things. Yeah, I mean, yeah, so why do we study computer science? I mean, it's okay, yeah, we make a difference to the world and all that. But, and it is true, yeah, and I hope we make the difference in the right direction. Yeah, but, sometimes a 40-year-old algorithm comes in unexpectedly in the middle of a question, and it gives you joy. So that is another reason to study computer science. Thank you.
So, are there any questions from the audience? Yes.
Yeah, question.
Hi.
Thank you.
In the medicines that you had AS and BS,
Yes.
BS appeared to be more constrained in the sense it should have been increasing both row wise and column wise.
Well, good, very good, very good. Yeah. So usually Young's tableau, when they are discussed, things increase left to right and top to bottom. This one, sorry, what happened? Yeah, this one seems to increase like this and increase in both ways. This one increases like this and, decreases like this and increases like this.
So the same formula will apply.
You just, you take a mirror here, now we are going into physics, yeah, and reflect it. And increasing will become decreasing and the same problem. So, yeah, thank you. Yeah, so I blindly said the same formula applies, but the two matrices are not of the same type, but increasing can be converted to decreasing just by reflecting. Yeah, thank you. Good question. Yeah. Yes, question. Yes, please.
Hello.
You're audible to me, but there are people on the net, I think, so you need to use the mic. Yeah, keep your mic. Yeah.
So the question is, in all these, we have been talking about strictly increasing and strictly decreasing sequences, right?
Yes.
So what happens when we relax that, and yeah, so how do things go there?
Yeah, so actually I don't know. So suppose I were to say that instead of k squared, if I allow your sequence to be increasing except for 1 or 2 elements. Well, if you allow 1 or 2 elements to be out of position, then, okay, so if you say that I want a sequence of length k plus 1, but 2 of them can be out of position, then you are basically looking for an increasing sequence of length k minus 1, and then you can just insert 2 more elements into it. So I'm not 100% sure, but I think considerations like that will just help you answer the same question using this analysis. I'm not completely sure. Yeah.
We have time for maybe one last question, if anyone.
Yeah, Gautam, yeah.
For arguing that columns are increasing,
Yes.
is the following alternate way of thinking meaningful?
Tell me.
A saturated sequence, when it is reversed, it is still saturated.
Yes.
When we do the same algorithm,
Yeah.
can we say now The rows are reverses of columns earlier?
No, the rows are not reverses of columns anymore. Yeah, that would have been very convenient.
Okay. Thank you.
Yeah. So, yeah, I must say one more thing. This RSK correspondence takes a sequence and produces two objects like this, two Young's tableau of the same shape, yeah, each row, etc., and puts data in the first tableau, and in the second tableau it records meaning where did the first element appear in the sequence, where did the second element appear in the sequence, and so on. So it gives you a correspondence, takes a sequence and builds two Young's tableau, okay. But in that Young's tableau, the first row is the longest, the next one is shorter, next one is shorter. Running the algorithm that we are taught by dynamic programming doesn't give that. So this RSK is a more sophisticated algorithm, yeah, but it achieves more. But for our baby problem, our dynamic programming algorithm is good enough, okay. And if there is any message, that is all there is in this talk, yeah.
Okay. So in the interest of time, maybe we will take other questions offline. So Professor Radhakrishnan will be here today as well as tomorrow. Just feel free to interact with him and ask him questions. And let's thank him again for the very clear talk.